important example here is a Hilbert loss function. You can see that the Hilbert loss function has a so it has a quadratic growth near the origin, but if the absolute value is beyond the threshold, then it has something like a linear growth. So this is some kinds of loss functions that has some statistical properties that might be used in practice. Another example is the so-called 2K byweight loss function, which with Clarkson and Woodruff recently we show how to obtain substance bindings for such loss function. So the loss function is basically has quadratic growth near the origin, but it keeps unchanged if the value goes beyond the threshold. So so for many different classes of loss functions and norms, we do have these kinds of substance bindings, and using these substance bindings, we can speed up the corresponding linear regression problem. So basically, if you change the loss function here to any loss function or norm where you have a substance binding, then you can speed up the calculation of the regression problem.
Your f can be a function of a or not?
Oh, I will mention this later.
Right now, no.
Right now, okay. So for which one?
Capital F can be a function of capital A?
For the definition, it can be, but yeah, in some cases, it will not.
Okay.
Yeah. Okay, so this problem is also studied in another different community in functional analysis. Well, functional analysts, they want to understand the structure of finite dimensional subspaces of the function space LP. So the function space LP is just a space consisting of all functions which the piece power, the absolute value, is integrable on the interval 0, 1. Okay, so one important question in the local theory of functional analysis is that they want to find the smallest number n, capital N, such that any d-dimensional subspace of the function space LP can be 1 plus epsilon embedded into, this is Rn armed with LP norm. So we want to find a linear embedding that maps each function in a d-dimensional subspace of this function space LP, and the norm is still 1 plus or minus epsilon approximated by the resulting vector. So we can see that this is closely connected with the problem of substance binding because the column space of any matrix, let's say there's a matrix of size n by d, and the column space of such a matrix armed with LP norm is indeed a d-dimensional subspace of the function space. So, so these two problems are closely related. And okay, so let's back to the problem of substance binding. There are 3 main known types of substance bindings. The first one is based on random projection. So if it is something similar to a Johnson-Lindström transform, where if you take S to be each entry or S to be IID Gaussian or random signs with roughly d or epsilon squared rows, then you can see this is the 1 plus epsilon substance binding. And the advantage of this substance binding, it is oblivious, meaning that it does not really depend on the A matrix that you want to embed. So it works for any A. But the drawback of this embedding is that, well, to apply such an embedding, it requires lots of time to do the calculation because projection is a dense matrix, and you want to calculate the embedding times the ordinal matrix. This will cost you lots of time. And this was later improved in a line of research trying to improve the time to apply such an embedding. And all these embeddings are still oblivious. Okay, so the second type of substance binding for L2 is the orthogonal basis. This is something special for L2 that can be only applied for L2 case. So what we can show is that if I take U here to be a matrix, orthogonal basis of A, then we can show that if you take S to be U transpose, then this is a substance binding with no distortion. Why this is true? Okay. So the reason is that, so recall the definition of substance binding is that for all vector x in the column space of A, for all vectors AX in column space of A.
U is A.
Right?
U is equal to A.
Yeah, U is equal to A.
Okay.
I want to show that this is actually the same as this one for all x. Why this true? Well, this is kind of simple because U is an orthogonal basis or A, so we can write any AX to be U times the changeable basis matrix R times X, right? And well, the left-hand side is U transpose times U Rx, and this is the L2 norm of Rx because this is identity. So for this guy, this is the URX, the L2 norm of URX, which is also the L2 norm Rx, right? So they are the same. So basically, this shows that if you take U transpose to be the substance embedding, then there is no distortion. Well, this has the advantage that the number of rows is only D, which is optimal even to have any finite distortion. But the drawback of this approach is that, well, calculating the orthogonal basis is very slow, and applying such substance embedding is also slow. So we cannot use this to speed up things like linear regression. And well, the third type of substance embedding is called row sampling algorithms. It's very intuitive. So if you want to preserve some kinds of good properties of matrix, one way is just to somehow sample a portion of the rows and show that they have the good property you want. And this is indeed possible to do. Where the best known way is to call sampling according to Larry scores. So what are Larry scores? They are just the squared L2 norm of the orthogonal basis U. Each row, okay, so you take orthogonal basis U, and you calculate the squared L2 norm of each row. These are just called Larry scores of these rows. And it has been shown that if you do some kinds of important sampling according to these Larry scores, and you sample these log the overlapping squared rows, then you can get a 1 plus epsilon substance embedding. So sampling according to Larry scores, it is non-oblivious because you need to first calculate the Larry scores of the matrix. So this is not something that is universal that works for all A matrix by a single embedding. But the advantage here is that actually because we are doing sampling, so we are selecting some of the rows and rescale them so that this might be some good properties that we want to use. We are actually choosing some rows from the original matrix. And here it is connected with spectral specifier. Well, if you just take A to be the edge vortex incidence matrix of a graph, then this is exactly a spectral specifier. Okay, so this is later shown how to remove this log D factor by a very famous work by this BSS spectral specifier. Okay, so these are what are known for L2. Are there any questions so far? Good. Okay. But what can we do for LP? We can still try to do the things we have done for L2. So we can first try random projections. Well, there are some constructions that are known for LP that are using random projections, replacing the Gaussian random variables with, or random signs with something called Cauchy random variables. But all these constructions, they have poly D distortion. Actually, the best known one has roughly D log D distortion. And so we cannot actually get 1 plus epsilon embedding. But can we improve this? Turns out this poly D distortion is somehow optimal, as shown recently by Woodruff and me, that any these kinds of random projection-based embeddings will have a poly D distortion. So this cannot be used to get 1 plus or minus epsilon embedding. Okay. So the second way we might want to try to do is something like what we have done here, to construct some kind of good basis and try to show that it can somehow preserve the norms of the vectors. Okay, and but LP norm, it does not have per second theorem, so you cannot actually use these kinds of good bases. So what kinds of bases have been known for LP? Well, there are at least 3 examples here. The first one is based on Jordan theorem, Jordan's ellipsoid. We can show that for any matrix A, you can find another basis matrix B such that the LP norm of Bx is, can be approximated by the L2 norm of X by a root D distortion. Actually here that we don't really need the LP norm. This works for any possible norm, so it doesn't really require LP norm. Second basis called Auerbach basis is something that the LP norm, you can find a basis matrix B such that the LP norm of Bx can be approximated by the LQ norm of X by a distortion factor of D. So Q is a dual norm of P here. Okay, so you can see that this joint theorem is not actually quite optimal for L2 because we know for L2 we can actually remove this root D factor, right? Because as I shown here, that orthogonal basis, it has really no distortion. And well, this is, so this can be somehow, we can somehow interpolate joint theorem with the case for L2 by something called Lewis basis, where we can show that you can find a changeable basis, you can find a basis matrix B such that the LP norm of Bx can be approximated by the L2 norm of X by a distortion factor of D to the absolute value of 1/2 minus 1 over P. Well, the good thing here is that, okay, so let's say if P is 2, then this is really no distortion, which matches what we get for orthogonal basis for L2. And when P is 1 or infinity, L1 norm or infinity norm, then this is exactly root D, what we get here by using joint theorem. So basically, Lewis basis is something that interpolates joint theorem and orthogonal basis for L2. Okay, but I mean, now these three methods will give you substance bendings because they all have some large distortion factors. So what we can do is we can try to generalize those row sampling algorithms to LP. Okay, so this is indeed the main way of obtain 1 plus or minus epsilon substance bendings. Currently, we are in theoretical computer science. We call these algorithms row sampling algorithms. And in functional analysis, there is a fancier name called changeable density, but they are actually roughly the same thing. They all refers to doing important sampling according to some kinds of scores of the rows. Okay, so the first result obtained in the CS community is by generalizing Larry scores to the LP case. So basically, as I mentioned before, Larry scores, Okay. So as I mentioned before, Larry scores are just the squared L2 norm of each row of this orthogonal basis. These scores can somehow measure the importance of each coordinate in the contribution to this to the L2 norm. So somehow inspired this approach, and using another basis, this Auerbach basis, we can show that we can use the norm of each row of the Auerbach basis as something called LP Larry score to do important sampling. And they show that if you sample this number of rows, a little bit messy, then you can get a 1 plus or minus substance bending. Okay, so as I mentioned before, this problem is also studied in functional analysis. And actually, functional analysis people are studying a marginal problem because they want to study a marginal class of space, the function space. And their results here also can give us some bounds. Okay, so the first result is it's got by Satchman. So he showed that we can sample D to the maximum of P over 2 and 1 plus 1 over squared rows to achieve a substance bending. And this bound was later improved by Bergen, Lindenstrauss, and Millman for the case when P is larger than 2, where they show that you can actually improve a D factor. So you can see that comparing these two bounds, when P is larger than 2, then basically the second one saves a D factor but has much worse dependence on epsilon. It has 1 over epsilon to the 5th when P is larger than 2. And the third result is achieved by Telegrand for the cases of P smaller than 2, where he shows that you can actually do near linear number of samples. So basically the number of rows you need to sample is D over epsilon squared. Here I'm ignoring lots of log factors and log D factors, log 1 over epsilon factors. So actually the bound here is d log d over epsilon squared for p equals 1, and the slightly worse log factors when p is between 1 and 2. Okay, I should mention here that all these 3 methods here are just based on sampling according to some kinds of scores defined using the Lewis spaces. As I mentioned before, Lewis space is something interpolation between joint theorem and orthogonal basis. But well, why cannot we just implement these ideas axiomatically? The difficulty is that we don't actually know how to calculate Lewis spaces, so we cannot actually get these important sampling scores. Okay, so another 2 constructions. Here there is one based on, well, here is one that works for only even p. So one is a even number, an even integer. So we can actually get an isometric embedding, meaning that there is no distortion. The number of rows you need to have is roughly d to the p minus 1. If we plug in p equals 2, then what we get is d, right? And this is exactly the second approach we get here for L2 case. So the approach based on orthogonal basis. Okay, so isometric embedding exists for even p, and recently by Sachman, it was shown how to improve the bounds by Bergen, Lindenstrauss, and Millman for even p, where he showed how to, roughly speaking, improving this epsilon to the 5th to epsilon squared. And also he shows all the log factors. His work is based on the very famous BSS spectral spacifier. Okay, so we can see something here, like all these embeddings for non-even p, they all suffer from a 1 over epsilon squared distortion. 1 over epsilon squared factors in the number of sampled rows. Another thing is that they all have a dependence on d to the p over 2, right? Okay, so natural question to ask is that are these 2 things necessary? And also very recently, roughly 3 years ago, Cohen and Peng showed how to actually get these scores used in this function analysis, used by these function analysis people. And they show an efficient algorithm to calculate the scores, and they call this Lewis weights. This is so using this approach, we can actually improve this bound by this earlier work, and we can actually achieve all these bounds that was achieved in functional analysis. So this is what we call the Lewis weights sampling. Okay, any questions?
What's a Lewis weight?
Huh?
What's a Lewis weight?
Oh, Lewis weight is just, okay, it's some kinds of, I mentioned that Larry scores are just the normal rows of the orthogonal basis. Lewis basis is something, between orthogonal basis and, something for LP, and the normal each row of Lewis basis is Lewis weights. Yeah, so.
Gary knows what a Lewis weight is.
No, I forgot.
Lewis weights for years.
I mean, like, yeah.
Haven't you?
No, I mean, at some point I know, at some point I forget. Because I think they're not trivial, right? I think the problem is
Yeah, like
paper is a tricky little paper to read. The Spielman.
Yeah, I mean,
Common Tang paper. Right?
yeah. I mean, they use some slightly different definitions, but it turns out these are just what are used in functional analysis. Okay, so far so good. So. Okay, so one question is that can we actually improve this dependence on p and dependence on epsilon? Well, what's the motivation? Well, let's say if we want to solve LP regression, if I increase the value of p, then I need to sample more and more rows. Can we actually do better? Another thing is that the dependence on epsilon is somehow bad. It has a 1 epsilon squared dependence on epsilon if p is not an even number. So if, let's say, epsilon is very small, then you need to sample more rows, and this might be bad in some cases. And all these constructions are based on row sampling. Can we actually improve these bounds by using other methods? So find some clever basis or whatever. So these are the questions. But before answering these questions, Well, let's first see why do we really need subspace embedding? Can we use something else? Okay, so let's consider the example of linear regression again. Well, let's say if I have some magic embeddings that can map LP norm to L2, or some other magic embeddings that can map LP norm to some function f, will this work? I mean, can it still help us to speed up regression algorithm? It turns out it can, right? Because if you can embed LP into L2, then you just need to solve a smaller L2 regression problem, which is also very easy to solve. And if this f function is convex, then minimize this is actually a convex program. We can still solve this problem, at least in polynomial time. And but you know, this instance is much smaller, so hopefully we can get something faster. So this really shows that we don't actually need the target space to have the same LP norm, but we can actually allow some other norms or other loss functions. Okay, so this is the first motivation for subspace sketch. And the second motivation is something we call distributed LP regression, which was first studied by Woodruff and Zhang, and recently restarted by Vampala, me, and Woodruff, where we consider the following model. So there are S servers, and there are some data. And these data are split among these servers. So basically, we can write all these data by matrix A. Each row is one data point, and each entry in this B vector is the label of this data. And suppose that these data are split among all the servers. So you can see that here, the first server S1 holds part of the rows. The second server holds another portion of the rows. And these servers can have point-to-point communication. They can send a message to each other. And we want to collectively solve this large LP regression problem. Right, and want to minimize the total communication complexity, meaning that the total length of the messages sent by these servers. What can I do? Well, some very simple solution using the notion of subspace embedding is just the following algorithm. So I first choose some guy special. I call it a coordinator. This is some guy special. And each server, let's say I'm S1. I look at my rows, and I obtain a subspace embedding for my rows. Let's say these rows are A1, B1, and I got a subspace embedding called S1. I just send this S1A1, S1B2, S1B1 to the coordinator. And then the coordinator solves this problem. And I claim that this will give you a approximate solution. Well, the reason is because the LP norm, if you take the piece power, then it has a nice additive structure. So basically, you can combine different parts together and to get a subspace embedding. Okay, so this is another application for subspace embedding. But here, let's consider again: do we really need a subspace embedding here? To minimize the communication cost, actually, what we need is something that can compress the matrix and preserve the LP norm of all vectors in the subspace. So we don't really need an embedding, but just anything that can preserve the LP norm of all vectors in the subspace will be sufficient. Okay, so these two examples lead to our new definition called subspace sketch, where we assume there are two functions. The first function is a compressed function that can, so it receives the matrix A and somehow compress it into a sketch M. You can think M is just some kinds of binary strings. And another function called recover, which should receive this sketch. It can recover the LP norm of AX. And we see this a pair of compress and recover is an LP subsketch. If for all vector X, if you first compress the matrix and then try to recover the LP norm of AX, then you will get a 1 plus epsilon approximation. Right, so this is actually some kinds of information theoretical version of subspace embeddings, where the goal is not to minimize the dimension, but we want to minimize the number of rows to do the compression.
So all the stuff you talked about so far solves this problem, but you want us to do it differently? I mean, all the stuff about compressing the number of rows in A?
Yes.
That all does what you want, but you want to consider more general.
Yeah, more general case.
So everything you've said so far applies to this?
Yeah, sure.
Okay.
Yeah. Okay, so now the goal is to minimize the number of bits of M. Okay, so what will be a good subspace sketch? As Gary mentioned, any subspace embedding will be a good subspace sketch, right? Because it also provides a way to recover the LP norm all vectors in the subspace. But there are a few other examples that are some are trivial, some are non-trivial. Okay, the first thing I want to show is that A transpose times A is a L2 subspace sketch with no distortion. Is that clear? Yeah, this is actually very simple because, well, the squared L2 norm of AX, what's that? Well, this is just X transpose A X, right? So if you have A transpose times A, then you can just plug in this quadratic form and you will get the square L2 norm of the vector. Right, so A transpose times A is a L2 subsketch with no distortion. Okay, and the second example is a generalization of this A transpose times A idea. Well, actually the idea is the following. So we can generalize this A transpose A stuff to any even integer P. Well, the rough idea is the following. So if you have a vector X, and you obtain another vector Y, you raise each entry to the P over 2's power, and we know that the squared L2 norm of Y is exactly the LP norm of X to the P's power, right? But on the other hand, this Y vector comes from a D to the P over 2 dimensional subspace, and you can just use the A transpose times A idea again to get a subspace sketch for this D to the P over 2 dimensional subspace, and so we can recover the LP norm of all vectors in the subspace, and the total number of entries you will have is D to the P, which is roughly the number of bits we get here. Okay, and this only works for even integer P. And the third example is the following. So let's suppose T is a matrix with IID Cauchy entries. If you don't know what is Cauchy random variable, don't worry, I will not get into details. And we can actually show that T times A is L1 subspace sketch if T has D over epsilon square number of rows. And what's the total number of entries we need to solve? Well, this TA matrix has the number of rows is D over epsilon squared, the number of columns is D, so it's D squared over epsilon squared. So you need to somehow store this number of bits. The recover function is a little bit strange here. It is, if you want to recover the LP norm, L1 norm of AX, then you apply this median function, which is you look at the coordinates of all the vectors, all the coordinates of Tx, you find the median of the absolute values of these coordinates. And we can show that this is a L1 subspace sketch. Something I want to mention here is that if you apply TA as a subspace embedding, so basically if you want to use the L1 norm of Tx to estimate the L1 norm of AX, then this will incur a poly-D distortion because T is a random projection. As I mentioned before, random projections, they will have polynomial in D distortion, which is not avoidable for L1 case. Okay, so these are a few examples we have mentioned here. Any questions so far? Okay. So our main result is actually a bunch of lower bounds. Okay, so the main results we have is following two things. For any LP subspace sketch with constant distortion, let's say 1.1, then there is a D to the P over 2 plus 1 lower bound. What does this mean? Okay, to understand this, let's first get back to the bounds. These bounds. Well, let's say if epsilon is constant, and we use this Born-Linus-Strauss-Milman result, so we can get subspace embedding with D to the P over 2 rows, right? And well, how many entries do I need to solve by using this embedding? I need to have an extra D factor because SA is a D over 2 by D matrix. So the total number of entries is D to the P over 2 plus 1, right? Okay. So this means that this D to the P P over 2 plus 1 lower bound is actually tight for even if you just use subspace bindings. So it means that even to compress the LP norms of all vectors in the subspace, this d to the P over 2 is kind of unavoidable. You must pay such a factor. And also, as I mentioned before, all subspace bindings are subspace sketches. This also implies a non-invalidability result. But here, the hardness actually comes from the fact that we cannot compress the matrix. And well, there are some similar results obtained in functional analysis before, but the way they show hardness is the following. So basically, the most classical way to show lower bounds is that I first show that if I have the vector space Rd armed with L2 norm, then if I want to, let's say, if I want to embed this vector space Rd armed with L2 norm into LP, Rn with LP norm, the n needs to be at least d to the P over 2. This gives us some similar results. And then how do they show the lower bound? They show that this space is actually contained as a d-dimensional subspace of the function space LP. So this implies a non-invalidability result from this function space to this vector space. But here, like you can see that the hardness really comes from the geometric structure of this target space. But here, our results comes from the fact that you cannot actually compress the source space. Right? So this is actually somehow stronger because it actually shows that you cannot use any possible functions to approximate the LP norm of vectors in the subspace using much less bits. Okay, so this is the first result. The second result is we show a 1 epsilon square dependence on epsilon. This is more surprising because actually before our work is unknown that well, even in functional analysis, it is unknown that whether this dependence on epsilon is necessary or not. We don't know whether we do need such epsilon dependence. But on the other hand, we do have some asymmetric embeddings for even p. So let's look at the lower bound we get again. What we showed is that when p is not an even integer, then this 1 epsilon squared lower bound will apply. As I mentioned before, this also implies a non-invalidability result. So this actually shows that, okay, so even for those functional analysis people, they cannot embed d-dimensional subspace of a function space LP without having this 1 epsilon squared number of rows. Okay, so if I have time, I will talk about some limitations, some other applications of our lower bounds. They will have some implications on the sample-based methods. Okay, so any questions about the results?
So this requires that you store your information as a matrix. I mean, you couldn't do error correcting codes or some other kind of data compression thing.
Yes.
Right.
Okay. Okay, so let's get into the technical parts of our proof. How can we show this lower bound? And actually, because actually our definition for subspace sketch has a communication nature, so one natural way to prove this is by communication complexity. And well, let's first show a d to the P over 2 lower bound for constant distortion LP subspace sketch. And what's the idea? Well, the idea is actually very simple. Well, let's see. We can construct a set of vectors with size d to the p. They are all sign vectors. All the entries are plus or minus sign. And another constraint that each of them, each pair of these vectors has small inner product. Why can we do this with just a simple Chernoff bound and union bound? You can show that such set of vectors will exist. Right? This is just a probabilistic method. Oh, by the way, this log defactor is not actually necessary. You can improve this log defactor by using some more advanced constructions based on coding theory, I think. Okay, but this is not important. Well, let's see why there's a communication lower bound. Well, let's consider the following case. Let's assume there are two players, Alice and Bob. Alice is a player who holds the A matrix. Recall that in the definition of the subspace sketch, there is an A matrix that you want to preserve the information about it. And Alice is the one who has this A matrix. Right? And how does Alice design this A matrix? She chooses n rows from the set of vectors we constructed using probabilistic methods at the row of this A matrix. Well, let's consider the case, what will happen if Bob query all vectors in this set of vectors, the D to the P vectors we have constructed. Well, if S is one row of A, then we can see that the LP norm or AS will be larger than D, right? Well, this is because that you have this A matrix, and the vector S you are querying is the same as one row of the vector. And we know that the inner product will be exactly D because the vectors are signs. So in one case, the resulting LP norm will be larger than D. And on the other hand, if you take n to be smaller than D to the P over 2, then if this vector is not a row of any rows of A, then the resulting LP norm will be smaller than this quantity. And if you carefully choose n, then we can separate these two quantities, meaning that actually Bob can know all the rows that are in this A matrix. Right, so now we can just get a lower bound because that they are basically the size of S, choose n different possible A matrix, and the Bob can distinguish all of them. So basically, if you take the logarithm, then this is a lower bound that we have as a communication lower bound. Okay, so any questions about this? Okay, but this is actually tight because we know the tight bound should have another D factor, and I will not have time to get into.
The lower bound is for dense matrices. Is that right?
Yes, in our construction.
Sparse, then it's not clear how.
Yeah, it's not clear. Yeah.
That's
Yeah, because for our matrix, the size is D to the P over 2 times D, right? If the number entry is smaller, then you can somehow do some clever ways to compress the matrix, right?
Okay.
Yeah. And well, the D to the P over 2 lower bound is based on some other more clever observations, which I will not have time to get into. And let's talk more about the dependence on epsilon, because this actually implies lots of new non-invalidability results in functional analysis. And I think one of the major difficulty here is that, okay, so suppose I have a proof that works for P equals 2. Why should not our proof works for, let's say we have a proof that works for P equals 1. Why should not the proof works for P equals 2? But we know that this proof should not work because when P equals 2, 4, 6, 8, there are actually isometric embeddings as upper bounds, so that this 1 squared lower bound should not actually hold, right? So what's the special thing here about even numbers? Well, it turns out that this is somehow related to Fourier analysis. Okay, so let's first sketch a 1 over epsilon lower bound. This is not tight, and but this has gives us the intuition of why there should be a lower bound. Let's consider the following construction. The dimension of the vectors are d. It is roughly log 1 over epsilon. And suppose there are a bunch of vectors coming from signs. All the vectors are signs. And recall that the A matrix, it has size n by d. And how does Alice design this A matrix? Well, she look at all the vectors with signs, and she include each vector with probability 1/2 into this A matrix. So basically, there are 2 to the d possible vectors, and roughly Alice includes 2 to the d minus 1 of them, right? Because she includes each vector with probability 1/2. And then Bob queried all vectors of this sign, or query all these sign vectors as the vector x. So he basically queries all ax for such x. And what I want to mention here is that if this 2 to the d times poly d is smaller than some small constant or epsilon, then in this case, Bob can exactly recover the L1 norm. Oh, so here I focus on the case of L1, but we will see how to generalize this to LP. So if this holds, that claims that Bob can actually know the exact L1 norm of all vectors in the subspace. The reason is that, well, we can see here that because this A matrix has size 2 to the d by d, and each inner product is bounded by poly d because each entry is this sign vector. All the entries are these signs. So actually, well, the largest L1 norm that is possible is 2 to the d times poly d. But we have relative error 1 plus epsilon, right? So if this if this relative error is small enough, and we know that all these L1 norms are integers, so Bob can exactly recover the L1 norms. So let's first assume this holds, like we do have a constraint that 2 to the d times poly d is smaller than some small constant times or epsilon. Well, let's view the things that Bob did in another form. Well, let's define the following matrix. It is a 2 to the d by 2 to the d matrix, where the entry on the ith row and jth column is the inner product between I and j, and taking the absolute value. Well, here I assume that the rows and the columns of this M matrix are indexed by these sign vectors. So this is some matrix, has size 2 to the d by 2 to the d. And let's define another vector which I call the characteristic vector, which are just the random points of Alice. So basically, if Alice includes a specific vector I, then I set the corresponding entry to be 1, otherwise it's 0. Okay? And I claim that what Bob receives by querying all vectors with this Boolean, with these signs, he just receives this M matrix times the characteristic R. Why is this true? Well, because let's say, suppose that Bob queries the vector I, and what he will get is just the inner product, the L1 norm of AI. But we know that A is just a subset of all vectors of signs. And if it is included, then this R is 1, otherwise it's 0. So this exactly characterizes Bob receives by querying all the vectors. Okay, so how shall we prove a lower bound now? One question is that what's the rank of this M matrix? I know there are some Boolean function expert in this room, so to make sure this is not a trivial problem. Ren, do you know the answer? D? No, it's extremely larger than D. It's actually exponential in D. Well, why this is true? Well, let's first say if I do know the rank of M, then what will happen? Let's assume that the left up corner of this M matrix is non-singular. And Alice just includes these rows with probability 1/2. And I know the characteristic vectors is just 0, 1 here. And what will Bob receive is just this large matrix M times this R vector. And the resulting vector, we know that the first rank M entries will just be M prime times this R prime vector. The other entries will be 0. But this M prime matrix is non-singular, meaning that Bob can actually recover this R prime vector by just solving a linear system. So basically, he can recover all these R prime random coins held by Alice, so there should be a rank M lower bound. Right, so now the question is just to study the rank of M, and I claim that the rank of M, well, the eigenvalues of M are just the Fourier coefficients of the function of the following function. It is d minus the Hamming weights of x. Here x is defined on, right, so each entry is 0 or 1. And the Hamming weight is just the number of ones in this x vector. So I claim that the eigenvalues of M are just these Fourier coefficients. If you don't know what are Fourier coefficients, it doesn't really matter. We just need a definition. Right, so why this is true? Well, this is actually a simple calculation. If you realize that, right, so the eigenvectors of this M matrix are just all the hard-marked, just all columns in the hard-marked matrix. And this is actually just a calculation. You can show that these are actually the eigenvectors. But if you do the calculation carefully, then you will see that these Fourier coefficients will be their eigenvalues. The Fourier coefficients is just defined to be, I do a summation over all the on the Boolean cube, meaning that each entry is 0 or 1. And I calculate fz, the summation of fz times minus I to the inner product between z and j. These are the Fourier coefficients. And we know that the number of, the rank of a matrix is just a number of non-zero eigenvalues. So the problem now is really how many eigenvalues are non-zero, right? And okay, so now we need to study the Fourier coefficients of this function. And we can see that there are lots of symmetry here. That this function really only depends on the Hamming weights of the vector x, meaning that it only depends on how many ones do we have in this vector.
Summation of entries I.
Sorry?
So each eigenvalue has multiplicity, something like entries I?
Yeah, exactly. But there can be some coefficients similar even if they belong to different Hamming weights. Okay, so as just mentioned, right, so if we set J here to be all vectors with Hamming weight exactly d over 2, so basically there are half of the entries are 0, half of the entries to be 1s. Because of the symmetry, we know that all these eigenvalues are the same. And if we can show that they are actually non-zeros, then we can prove a lower bound on the rank, and which will imply a communication lower bound, which also implies the lower bound for subspace sketch and the non-embeddability result. And well, this is just a calculation. There will be lots of binomial coefficients here, and what we will get finally is that we will show that the Fourier coefficients will be larger than 2 to the d over 2 over root d. And also, as we have mentioned, because the symmetry here, these Fourier coefficients really only depends on the Hamming weight of this j. So basically, we have d choose d over 2 Fourier coefficients which are the same. But we have shown that all of them are non-zero. So there are at least d choose d over 2 eigenvalues which are non-zero. So meaning that the rank of this matrix is at least d to the 2 to the d over root d. D choose d over 2, which is at least 2 to the d over root d. Right? Okay. Okay, so plugging in all these things, we will have 1 over epsilon lower bound. But the question here is that why will our argument fail for L2? The magical thing here is that, well, if you change L1 into L2, so basically you need to study the Fourier coefficients of another function to another piece power. And we have studied like these eigenvalues, what I call the middle eigenvalues, because they are the Fourier coefficients associated with degree d over 2. And if you calculate them, well, actually, I don't know how to calculate them, but I can plot them. This is a plot. These are the Fourier coefficients. You can see that this function magically vanishes if p is 2, 4, 6, 8. And otherwise, it is non-zero. So if it's non-zero, then we know a lower bound on the rank, and we will have a lower bound. But if it is even numbers, we will see that this will be 0, and we should not have a lower bound. But this should be the case because we have an upper bound. So actually, this magical function characterizes why should we have asymmetric embedding when p is an even integer, and otherwise we should not have. And okay, so I don't know how to do this, and we all don't know how to do this, how to lower bound the Fourier coefficients, because there are some very hard binomial summations. But finally, we find something that was also studied in math, where people show that these Fourier coefficients will be larger than 2 to the d over root d times this sine p pi over 2 function. So this actually explains why this function will vanish when p is an even integer because of this sine function. So when p is even, this will be 0, so we don't have lower bound, and this should be the case. Okay, I don't have time to get into the one-weapon square lower bound, but just some more clever ideas and error analysis. Okay, so let me conclude the talk. Right, there are lots of things here. Okay, so we get a lower bound of dependence of subspace sketches for dependence on P and dependence on epsilon. And this also implies lots of non-embeddability results for the functional analysis problem people studied. So some questions, open questions here is just, can we get tighter bounds for subspace embedding and subspace sketch? So one thing that is not tight here is that we do have separate lower bounds for P and epsilon, but can we combine them to get a tight bound? Like has both dependence on P and dependence on epsilon. And also, actually, we don't know any advantage of this new subspace sketch model that can go beyond subspace embedding. So the best things we can construct for the subspace sketches are just subspace embeddings. So can we show some separation between subspace embedding and subspace sketches? All these things are actually the same. I don't know how to solve this. And the third open question might just be, will these subspace sketches have more applications in other scenarios? Okay, so that's all. Thank you.